What we're going to do in this video is we're going to start our unit on population standard deviation and variance. What you want to remember is the standard deviation is the square root of the variance, and it's very important when we go to StatCrunch that you notice that StatCrunch deals with the variance. So if you know the standard deviation, you need to square it for the variance. So that's what we're going to do here today. So we're going to look at section 7.3. So let's continue. What we're going to do is the same thing that we've done with the population proportion and the population mean. We're going to come up with a point estimate, and the sample variance is the best point estimate of the population variance. We're going to talk about confidence intervals in this section as we look at standard deviation, and we're going to use the chi-squared distribution. So now this is pronounced chi. If you're a student at a university, this is like the sweetheart of Sigma Chi, the fraternity. So it's not a chi square, it's a chi square. And so what we're going to do is we need to come up with the chi-squared sample statistic. And you can see here is our equation. So we're going to talk about our chi-squared distribution, and it's a ratio between our sample variance and our population variance. So when we have a critical value of chi-squared, we have two critical values. We have the right tail and we have the left tail. And the reason for this is our chi-squared distribution is not symmetrical like our standard normal distribution. So we use degrees of freedom, and degrees of freedom is equal to n minus 1. And here is our chi-squared distribution. As you can see, it's not symmetric. So it's different than both our standard normal distribution and our student t distributions. Notice it starts at 0 and it is skewed to the right. So chi-squared values can be 0 or positive, but they cannot be negative. Now, as our degrees of freedom get bigger, and what that means is, since our degrees of freedom are the number in our sample minus 1, the bigger our sample, the closer that distribution comes to being normal. It's not symmetric, so we cannot write it like we did our other confidence intervals, minus a margin of error plus a margin of error. So when we do this, so we have to do separate calculations for the upper and lower confidence interval. We're going to see how to do them by hand using table A4, which is in the barrel fold tables you find in your textbook. It's also in the tables that I sent you. I posted in the resources folder. The other thing is the table is also in the back of your book in one of the appendices. In Appendix A, we're looking for table A4, and if you want to look at that in your book, that is on page 687. All right? But use those tables that you printed out, or we're also going to use StatCrunch. Now, the thing about table A4, which we will look at in a moment here, is the area at the top is the cumulative area to the right of the critical value. In fact, I'm going to table A4, and so what we have is we have the area to the right. So we have the areas in the upper tail. We have the areas would be to the right of the upper tail here on the left side of the table, and we have areas to the left of the lower tail on the right side of the table. And we'll talk about how to use this in just a bit. So we're going to use an example that's in your textbook, and it's example 1 on page 334. So we have a simple random sample of 22 IQ scores, and we want to construct a confidence interval for their population standard deviation. And we want to use it at the 95% confidence interval. Now, why would we do something like this? Well, we're going to do something like this because we want to know about the sample variance. So if the sample has a variance that is close to the population variance, the value of chi-squared will be close to the number of degrees of freedom because it's a ratio. And so when we square anything, it's always a positive number. So our sample standard deviation, our sample variance is our sample standard deviation squared. That's going to be positive. Our population standard deviation squared is going to be positive. So chi-squared will be positive. So that's why the chi-squared table starts at 0. Now, the standard deviation of our samples can tell us a lot of information. So here we go. Here is our table, and you can see we had 95, confidence interval of 95%. So that means the 5% outside of what we're interested in will be split between the lower tail and the upper tail. We're going to use degrees of freedom of 21, and we're going to look for the cumulative right area of 0.975. We're also going to still use degrees of freedom of 21, and we're going to use the cumulative area at the top of 0.025. So what we have here is we're going to look at these values, and we're going to see how we do them on the table, and that's going to be the next. So we find our 2 degrees of freedom using the table. So let's go to the table and let's look at that. So what I'm going to do is because I have 22 in my sample, I'm going to use the 21 degrees of freedom row. I kind of got off there a little bit. So now I'm going to look for 0.025 over here. That would be the upper tail. And when I go down there, that's how I get 35.479 for my critical value there. In my left tail, I'm going to use the 0.975, and when I go down there, that's how I get the 10.283. Okay? So that's how that works. So we're going to construct that confidence interval, but we have to look at our vocabulary, which we've done in all the sections we've done up to this point. So remember, sigma is the population standard deviation, sigma squared is the population variance, S is our sample standard deviation, S squared is our sample variance, N is the number in the sample, E is the margin of error, but that's not the same both top and bottom, and we have our critical value to the left and our critical value to the right. Here's what has to happen. Again, that very important thing that it's a simple random sample. And I will tell you that the population must be normally distributed, and that's more strict here than it was for population proportion or a population mean. And here's the formula. So n minus 1, that's our degrees of freedom. S squared is going to be our sample variance, and then we're going to use our critical values, both right for the lower and left for the upper, to get our confidence interval. And then if we want the confidence interval for the standard deviation, we take the square root of both of those. Here are our round off rules. When we're using data, the original data, we go one more place than is used for the original data. So if original data goes to hundredths, we take our interval to the thousandths. If we're using summary statistics, we round to the same number of decimal places used in the sample standard deviation. So we need to verify that the two requirements are satisfied, find the two right and left critical values, and then plug that into our equation to find the confidence interval. And if we're looking for the estimate of sigma rather than, or it's the standard deviation, which is sigma, rather than the variance, which is sigma square, we simply take the square root. Okay, now here's the deal. These confidence intervals can be used to compare the variation in different data sets, but overlapping confidence intervals should not be used for making formal and final conclusions about the equality. We will do that when we do the significance testing. So in Appendix B, there's a data set, and if you want to verify this, you can find this data set in StatCrunch under data sets from the book. And we have IQ scores in 3 different lead exposure groups. We're going to look at the 22 full IQ scores with the medium exposure to lead, which is group 2. And we found, using StatCrunch, that their standard deviation, that's S, is 14.29263, a 95% confidence interval for the standard deviation. Okay? So the first thing we did was we're going to treat this as a simple random sample, and then we use StatCrunch to make a histogram of the data, and it's relatively bell-shaped, relatively symmetrical, so we're good to go. So now we're going to go back to table A4. And when we do that again, we had 22 in our sample, so we're going to use degrees of freedom of 21. And we're going to look in the columns of 0.975 and 0.025. So we know we still have 21 degrees of freedom, and we're going to do 0.975, and we're going to do 0.025. So we get the same critical values that we had for our example. Okay, so that's what we have. So now we're ready to do the math. So we're going to plug this into our equation, and remember this n-1 is our degrees of freedom. Now look at what we have to do. We have to square S to use this because we're finding the variance. Okay, that's what our equation does for us. So we do the math and we come up with this for our variance. So our variance, we're going to estimate it to be between 120.9 and 417.2. Okay, now we used a real data set here, So I'm going to assume that the data was reported to the nearest whole number because we reported this to one decimal place. But we didn't want to know what the variance was. We wanted to have an estimate of the population standard deviation. So we're going to take the square root of both sides. So the standard deviation of our population is somewhere between 11 and 20.4. So we have 95% confidence that the limits of 11 and 20.4 contain the true value of our standard deviation. Now we can put it into that notation with the parentheses, but we can't do it in the plus or minus. Okay? And to be honest with you, I really think that S should be, I think it should be a sigma, because we're estimating the sigma up here. So again, we can't use an S here, but we can use sigma. Okay? Okay, let's look at StatCrunch, and I'm going to look at StatCrunch to do two different things. So I'm going to use StatCrunch to find my critical values that we would put into our formula, and then I'm going to use StatCrunch to find our upper limits and lower limits. So let's look at this, and I'm going to go Stat Calculators first. I'm going to go here to chi-squared, and I'm going to look at the standard, and I'm going to put in my degrees of freedom. And remember, we had 22 individuals in our data set, so our degrees of freedom would be 21. I want to find what the value of my chi-square is if I had 0.025 to the left, and when I do that, I get the same critical value, 10.283 it would round to. And then I can do it again and do 0.975 here. And when I do compute, I'm going to get the 35.479 that we got off the table. And then I can go and I can do the same thing that I did before. Okay, let me show you how you do everything in one fell swoop. You're going to use the between button here. And I'm going to, you can get these would be the critical values. I'm going to just do, so I'm going to put 0.95 between two values, and I get both critical values in one fell swoop. Okay? Now, let me show you how you get the confidence interval. I'm going to go stat, but this time I'm going to go down to variance statistics. Right now we're doing one sample, and we're doing this with summary right now. And our sample variance, this is where we have to square that value from our sample. So our sample, and let me pull this in here. So you remember that our sample standard deviation was 14.29263, and we're going to square that. So you can see I'm going to get 204.2792723. Okay, now that's what I'm going to put in here for my sample variance. 204.2792723. And then my sample size was 22. Now I'm not going to do a hypothesis test yet, but I'm going to do the confidence interval. But remember, it asked for this sample variance, so I must square my sample standard deviation. My confidence level is 0.95, and so now I'm going to hit compute. And you can see there are our upper limits and our lower limits, just like we found on our slides. And we were asked to find not the variance, which this is, we were asked to find the standard deviation. So then we would take the square root of 120.91321 to get 10.99, which would round to 11.0, and then we're going to take the square root of 417. Can I do this? 0.18442, and I get 20.43 or 20.4. That's what we got earlier. Okay, see how that works? And on page 339 in your textbook, if you haven't found these at the end of the chapters, is a text center that tells you how to do each of these things. And so there's the stat crunch, the directions, and so that's exactly what we did. But you need to remember that we're always doing the statistics, we're calculating for the variance, so if you have the standard deviation, you must square it. Determining the sample size. This is more complicated than it was with the mean or the proportion. So what happens is we get tables to do this. So if you are following along with this in your textbook, the tables you can find on page 338. Now I'm going to give you a hint. Since this next exam is taken with a proctor, you won't need these tables, but to do your homework you will. Now you can use this formula, but it doesn't tell me what D is. So the formula doesn't mean much, does it? But here are the tables. So if we want to have a 95% confidence interval, here is the table that we're using. So if we want our standard deviation to be within 5%, we should have a sample size of at least 768. If we want to be 99% confident at a 5%, to be within 5%, then we need at least 1,338. So those are going to be the tables you need. They're on page 338 in your textbook. You might want to do a little cut and paste or print out these two slides so you have those when you're doing your homework. So let's do an example. So we want a 99% confidence interval. We want to be 99% confident that our estimate is within 5% of the true value of our standard deviation. How large should our sample be? And we're doing this very important assumption that the population is normally distributed. So we're going to use the table. And you can see that when we go to that table, we should have 1,336 IQ scores from the population in our sample. Let's just go back a little bit and let's look at this. And we had 22 in our sample, so we can only be sure that our estimate of the the population standard deviation is within 30% of its true value. Not very close. So the bigger the sample, the better your estimates will always be.